Today we have this converter. It's a 12 volts to symmetrical output power supply, plus or minus 24 volts power supply. That's about 150 grams. It's about 83.6 mm, 75, 83 to 75, 83 by 75 mm in size. So the output capacitor is 1000 microfarad, 63 volts. These are all Chongx, Changsen. This one is Cheng, Chong. This one is Chong. So the input capacitor is how much? 2225 volts. So it got a nice size transformer here. The coils is, yes, it's moving. You can see it there. So that's not good. Because they can rub against each other. This is the output rectifier. That's a small heatsink. Could not read that properly. It's hard to read. Okay, so it's time to test this converter. This can be used to power some small amplifier like TD7294, 7293, LM3886, but you will be limited to plus or minus 24 volts. And also this converter is, the output is not regulated, so the output will vary with the input voltage. So if the input voltage drops, the output voltage will also drops. I got the converter hooked up to our electronic load, connected to our electronic load. This is our 12 volts power supply. We have 230 volts input, 50 hertz. This meter here is connected to current. We're going to use this to measure the current going to the converter. This multimeter is connected to the input here. And we have another multimeter here. It's connected to the output of the power supply. So we're going to take these measurements. We're going to compute the idle power, and so in order for us to compute the idle power, we need the input voltage and the input current. So our input voltage is here, 12 volts, and this is our current. So these are output, I mean the idle power. To get the idle power, we need to multiply the input voltage and the input current, and that's the idle power. Now we're gonna turn on the electronic load. We're going to put a 1 ampere load. Okay, I already set 1 ampere. It's there, 1 ampere. Turn it on. So our input directly to the converter has dropped to 11.88 volts. There's about 0.12 volts voltage drop in this current sensor. So we're just going to increase the input a little bit to 12 volts. In order for us to do that, we have an adjustment here. Oh, I really hate this Anning multimeter. It has a timer, and it cannot turn the timer off. It's going to turn off by itself even if it is in use or it's turned on. Okay, so that's 12 volts input. That's directly to the input of the converter, and this is the output of the power supply. So we have about 0.14 volts voltage drop here. So the output is around 20.5, 20. So we're going to can round this off to 20.6. So we have an output of 20.6 volts with a current of 1 ampere. Okay, so I have now recorded our output voltage 20.6 volts, output current 1, input voltage 12. Our input current is 3.7 amps. You can see there, it's 3.7. And our ripple, this is our ripple, peak to peak. (900 millivolt to 1 volt peak to peak). So this is our ripple. Now we can compute the efficiency of the converter at 1 ampere load. So this one is the output power and this is the input power. So we can get the efficiency by dividing the output power by the input power. So this is our output power, 20.6 volts times 1, 20.6 times 2, it's 41.2 watts. This is our output power. We need to multiply the 20.6 watts times 2 because we have two output. Remember, we have two output here, the positive rail and the negative rail, and this is our output power and this is our input power. So to get the efficiency, we need to divide the input versus the output. 41.2 divide 44.4. So the efficiency is around you can round this off to 93%. This is the this is our efficiency at 1 ampere load. Now we're gonna do the 2 amperes load. I forgot to show the no load output voltage of the converter. So that's our output, 22.3 volts. This is supposed to be a 12 volts to 24 volts converter. So that is our output, no load output. Gonna set our output to 2 amperes. The running has turned off again. Now we need to adjust the output. The output of the power supply. We need to adjust the output of the power supply to compensate for the voltage drop here. So we have a 12 volts input to the converter. Yes, that's 12 volts. And we have 12.28 volts output directly at the output of the power supply. So that's about 0.28 voltage drop in this setup in our current sensor. Our ripple is almost similar to the 1 ampere load. Still reaches more than 1 volt peak to peak. Now we're gonna move on to 3 amperes load. Currently set at 2 amperes. Turn it off first. 3 amperes. Okay, so the output drops to 19.6. The input current going to the converter is now 10.9 amperes and the voltage has dropped to 11.87. We need to adjust again to, so it will be exactly 12 volts. Okay, so that's 12 volts. And the output of the 12 volts power supply is now 12.4 volts. So there's about 0.4 voltage drop now in our current sensor. And the output has dropped to about 20 volts now. I can turn off the beeping of this meter. This meter keeps beeping. This is rated at 20 amperes but it's beeping at 10.9. And I can turn off the beeping. So I have now recorded the data here about output voltage 20 volts, then 19.9, round off to 20 volts. Output current 3 amperes. Here 3 amperes. and input current to the regulator to the converter 10.93 over there, 10.93. Now we can compute the efficiency of the converter at 3 amperes. So this is our ripple. 900 to still 1.16 volt maximum. It's almost little difference from 1 ampere to 3 amperes load. So we're going to compute for the efficiency of the converter at 3 amperes load. So this is our input power and this is our output power. So that is 120 divide 131, 91%, 91.6% efficiency, 91%. And the efficiency at 2 amperes load, 81.2 divide 87.7, so 92%. I'm just going to turn this off because the meter won't stop beeping. Okay, so this is our results with 12 volts input. The ripple is 900 millivolt to 1 volt with efficiency of 93%. And the output is 20.6 volts per rail, and at 2 amperes 92% efficient. Output voltage is 20.3, so a little bit lower. 3 amperes 91.6% efficient, and output is 20 volts. Ripple is almost the same, no difference from 1 ampere to 3 amperes. So this converter is good for 3 amperes load, that is about 120 watts. So you can use this to drive 7294 or LM3886, but you will be limited to symmetrical 20 volts power supply. Going to quickly see the output of this power supply at a little bit higher input voltage instead of 12 volts. This power supply can only output, the maximum output of this power supply is around 13.9 volts. That is the its maximum voltage output. So I'm gonna set this to its maximum voltage output, and then we're gonna check the output of the converter. I'm also going to remove this, so we're not going to have any voltage drop here. So let me adjust this so the output is, I just turned it on, it turned off again. So Okay, so I have removed the current sensor. So the input to the converter now is around 13.79 volts, and the input is this 13.9. so we still have around 0.11 volts voltage drop on this cable here. That is with 3 amperes load. The output has increased to around 23 volts, so we gained around 23 volts output compared to the 12 volts input. With 12 volts input, we have about 20 volts output. So with the 13.8 volts input, we have gained another 3 volts output, so that's a total of 6 volts, 3 volts each per rail. So the output of this one is not regulated, and the output depends on the input voltage. Next, we're going to test this one. This one is a little bit bigger than this one. This one has 2 driver transistors. This one has 4 driver transistors and 2 output rectifier, but the output is still unregulated. And also, I just got this one. This is the big brother of this one. So this one has a potentiometer here. Looks like the output voltage of this one can be adjusted.